Greetings, dear friends. Welcome back to my YouTube channel. Today, we are with a new video that is an addition to our, addition to the advanced module of Abaqus that we had started. I got quite a lot of requests for this video. This video is about implementing uh, Johnson Holmquist Concrete 2, that is, uh, that we call as JH2 model in Abaqus. So this model is actually not available in the graphical user interface of the software, but there are ways of incorporating this as a VUMAT, or we can say there are ways of invoking this material model when simulating concrete at some high strain rate loadings. So let's get started. Here I am presenting the original version of the paper that describes this concrete model, actually by the developers of the model. I'll share the link in the description where you will have an access to this paper. So this concrete model is really it's applicable to concrete or concrete like materials like ceramics, and it's applicable for the materials when they are subjected to large strains or high strain rate loadings and high pressures. So while simulating concrete under impact like situations, high strain rate loadings, or blast like situations, we can use this model or invoke this model in Abaqus. This paper describes this model as a whole, and you need to go through this to understand what the model is about. And this also describes the procedure for determination of the constants, or what are the constants that we need to find out. And the good thing about this paper is they've already computed these constants that we actually need in our simulations. These are the material models that we, rather constants that we need to, use for our simulation. We will be using these constants correspond to 48 megapascal or 0.048 gigapascal concrete strength, and these are the all the constants that have been determined, and we'll be using these in our simulation. So I'll request you to go through this model and understand what is the physics behind this model. But the primary idea of this video is to how to implement this in Abaqus. So here I've already simulated this. So let me go to the CAE file. So I have already two parts created. Part 1 is the concrete slab or a concrete panel, you may call it. Part 2 is a ball. So if you want to replicate this, I'll go through the steps again. This is the part 1, concrete slab. I have taken a 500 mm, 500 mm. I'm using the units of Newton mm, SI units, but Newton and mm. So you'll need to look at what are the other units that correspond to Newton mm when we are using, when we need to be consistent with the units actually. So you'll need to, I have already shared in other previous videos, like how do we use units in Abaqus. So we are actually using mm. We're working in mm. So we are using 500 mm, 500 mm this panel. And if you see what is the now the thickness is 50 mm. 50 mm, 500 mm, 500 mm is the dimensions of this slab panel. Now if we look at the part 2, part 2 is the ball. So I have, how did I model this? You're all familiar with the modeling now. I have gone to the 3D modeling, deformable, and then if I click on this solid, so I have used solid revolve. And I have modeled this sketch here. This is the construction line, and then I have modeled half of this circle, and after like drawing this half of the circle, you just need to define what is the angle for this solid revolution. I have specified 360, and we are done. We have created a solid sphere of 60 mm radius. After that, I have actually we can delete this for now. I have created a material known as steel, where I have specified the density of 7.8 into e power minus 9. It is when we are using Newton mm units, the mass density has to be in tons per mm cube. So this comes out to be 7.8 into e power minus 9. And I used elastic properties of 2 into 10 power 5 and Poisson's ratio of 0.3. These are the steel properties, elastic properties that I am assigning to this ball. I have created a ball section where I have assigned steel, and then I have a concrete as a section, but I have not specified any kind of material to it for now, because I'll be implementing, or I'll be using materials in the input file. That is the main part. After this assigning properties and all, I have created an assembly like this. This is the panel and this is the ball. You all are familiar with the modeling now, so you should be able to assemble it like this. It's exactly at the center of the panel at a distance of around, I think, 1 meter. So if you just if you want to check whether it's center, if you look at the top view, this is side view perspective. This again at the center this way, and side view. So it's exactly going to it's orienting along the center of the slab. After the assembly, you need to create a step, as already we know, and we have created a dynamic explicit step, and we have formulated a time period of 0.03. So for total time of 0.03, our simulation will run. So once you're done with the parts, created properties, assigned properties, created assembly, created the step where we actually specify what is the type of the analysis that we need to do. We also need to see what output do we need. Output, I have checked all stress, strain, displacement forces, and the most important, I need solution dependent variables. Since our model, we need various like parameters as a result, like damage or the volumetric strain or the plastic strain and all. So those are all given in JH2 model as state variables. Those are called as state variables. So we need to check on this state variable option here, and then in the interaction between ball and this slab or the panel, concrete panel, I need to create an interaction. If you see, first I need to create an interaction here, interaction property, where I have defined a tangential behavior and normal behavior, and I have given a coefficient of friction as 0.2. And then I have created a contact or interaction between the two as general contact. If you see, it's a general contact explicit, where I have used interaction property that I have already created. And then we need to define the velocity up to the ball and also the boundary conditions to this slab specimen, where I'm assuming fixed boundary condition. or restrained boundary conditions. If you go to this boundary condition manager, I have already one boundary condition already created. So this is encaster, that means fixed boundary condition across all the faces. If you see, these are all like faces restrained, right? And then for the velocity to the ball, what I'll do first is I'll go back to interaction. I want this ball to be reached. I have created as an elastic deformable, but there are ways of like making it a reached ball. Although we have given the properties, but if in case we model this impact phenomenon as a hard impact, we need to make this ball as a rigid. For that matter, we need to go to the constraint manager. Yes, we need to go to the constraint manager, rigid body, continue. Here, body, we need to select this ball as a body, right? Done. And we need to define a reference point or select a reference point. Like we are coupling this rigid body to some reference point. So for that matter, we go to the tools, reference point, and we'll define one reference point anywhere. So now escape. Now we need to select this reference point. Sorry, reference point. This is the reference point. Done. So what we did here is we created one constraint, body. In the rigid body, we picked this ball, and as this point, we picked this reference point. So what it will do is, once we give velocity to this reference point, it is as if we are giving velocity to whole of this rigid body. Now we need to give velocity. We will go to the loads. We'll go to, we have already defined a predefined, I'll delete it. So how to create velocity? So this is predefined field. We'll go to initial, mechanical velocity, and here I have defined the reference point. Right? And done. Oh, and we'll give, suppose, a velocity of minus v3. If minus is the direction, we'll need to give, suppose, minus 10 meter per second, or let's say 50 meter per second, 50,000 mm per second. That's 50 meter per second velocity, but in negative z direction. Okay. So we have given the velocity. Let's first not to get confused here. Two reference points got created. We'll delete one. We'll need to go to the assembly and features. We'll delete reference point 1. Both the reference point got deleted, so we'll create again reference point. Reference point 1. Now we need to go back to interaction, constraints, body. We have already picked reference point. We have now picked the correct one. Loading, we need to give velocity to reference point 1. So this velocity of 50 meter per second is actually applied to the whole ball. So what is the step after that? We are almost done with whole modeling part. We created a ball. We created this concrete panel, and then what we did was we assembled them. We created step, then interactions, and then load, and we have meshed it. You can mesh it as a tetrahedral. If you try to mesh this ball as a if you see what mesh I've used tetrahedron. If you use hexahedron, this may not work because it's a sphere and irregular kind of. It's not going to be hex or 8-noded brick element. So we need to use tetrahedron to mesh the ball. And we're already meshed and everything is done. We need to go to the job and we need to create a job of JH2. Correct? JH2. And once the job is created, what you need to do is you need to write an input. Let's first see where it is saved. Our set work directory will save it in JH2 concrete folder. C temp JH2 concrete folder. Right. And now we'll write an input. An input file is created. If we go to that folder, we'll need to go to C, then temp, then JH2 concrete. And if you see date modified, JH2 input file is created. This is whole model is created, right? Now comes the main part. How do we implement JH2 concrete model in this, in our simulation? What we'll do, I'll share this link also with you. This is a link that will take you to this page, high velocity impact of a ceramic target. This is again given by the Abaqus itself. So it says there are some two models, JHB and JH2, that can be used not in the GUI, but without GUI, like we will be able to implement these models. So if you see here materials, it says these built-in materials are invoked by material names with ABQ underscore JHB and ABQ underscore JH2. These are very important things to do. We need to name the material as ABQ underscore JH2 and then anything, concrete or anything you can name it. I'll show it how. First, what you need to do, they have already provided one input file for JH2, but it's for silicon carbide. It's again a ceramic material, but we are using concrete. Ours is a different input file, but we'll only take the material model out of it. So what we'll do is I'll click on this. Our input file got to open here. If you see, this is our input file that's given by the Abaqus. What we will do is we'll go to the materials. Yeah. We'll copy this part from parameter. Here he has defined some parameter. When we are using a parameter star parameter, it means we are introducing parameters by ourselves. Parameters, these are all the constants that we need to incorporate for concrete. Here it's given for some silicon carbide like material. What we'll do is we'll copy this up to here. Another material starts after that, gold, but up to this we need to copy this. We'll create a notepad file and we'll paste it. Now only thing we need to do is we need to replace these constants by our values that I had already talked about, like these. Our A is 0.79. For this material, it's 0.696 and all. So we need to incorporate these material parameters into this. So we already done it for you. So here it is. This is for M48 megapascal concrete. We have used this original paper, and these are all the material parameters that we have taken. I can, since this paper will be shared with you, so you should be able to you should be able to incorporate these material parameters. And now what you need to do is you need to copy whole of these parameters, go to the input file that we just generated using our Abaqus, this JH2, and go to materials. Material starts from here, and only one material is actually created, steel. Let's paste it over here. Now we have defined one from the materials here. You can just you can take a line parameter. We have pasted all those parameters here, and then our another material starts from here, right? And this material here, you must be very, very careful. This material is named as ABQ JH2 underscore concrete, right? And I need to use this material for concrete section. I'll copy this. I'll see where I'll find concrete. There should be a section. Yeah, section created. Section created, and material is named as, okay, fine, ABQ JH2 concrete. So it's already assigned to this section, this material. Fine. So you have to be very careful here. What I did was, from the material, this materials part, I have pasted parameters from here to up to this. These are all that we call as state variables that you'll be getting as an output. And then material steel we had already created and assigned in the GUI itself. If you try to open this file as like now in the Abaqus as like import as an input file, this will vanish because this is not available in the GUI. Then how do we really submit this file to Abaqus? If we cannot even import it and run it, how are we supposed to run it? So we can run it using command window. So what we'll do is, now we'll save it. JH2, we have saved this. If you see here, I open it. So it's already saved. Yeah. So you'll go to command window, you type cmd command window. You need to go to that folder first. Slash, you need to change the folder cd slash, it's a temp folder in raw cd temp, and the folder name is JH2 concrete. Concrete. Yeah, you are in that folder. Now you need to type a command like Abaqus job equal to, what is the job name? It is JH2. Fine. JH2 .imp, and you need to enter, or you can specify CPUs as well. But if you type enter, and it has removed the input file, and it's now started running. If you go to the folder, yeah, we're there itself. Now it started running. You can monitor it like JH2. This end of this has already finished. There are no errors, and it's now started running. This ODB file has got generated. And now what you'll do is you'll go to the Abaqus. You can open result file, this JH2 ODB. Since it may take some time, if we monitor this, it will take some time, and ultimately you'll get a file like full after finishing, after like simulation is done, you'll get a full ODB file like this. When you try to open it, it's like this. So here are these state variables I'm talking about. State damage state variables. and this is a ductile failure, this is volumetric strain, this is equivalent plastic strain, and all these all are, and you can see this is our simulation result. If you see, this is the crater at the top and this is crater at the bottom. So this way, this using this model has an advantage of like it takes care of high pressure a concrete is subjected to during high strain rate loadings, and a strain rate effect is taken care of. You might have been seeing, or you might have used a well-known concrete damage plasticity model that is there in the graphical user interface of Abaqus. But to be very precise, that's not applicable to high strain rate phenomena like impact or blast when we do not use strain dependent data in that. So this model also has some limitations if you just go through the theory of this, but for a range of velocities or for a range of blast loadings, this model works good. So you can simulate impact, you can simulate blast or any high strain rate like kind of phenomenon using this model. So I want to reiterate. At the end I'll recapitulate a bit. What I did was the main idea of this, like how do we implement this JH2 model, is you need to create an input file of your model. Once you model your paths and everything, interaction and all are done, what you need to do is you need to create an input file, and then in the input file, then in the this is .dat file, and then in the this is our input file, something like this. And then in the input file, you'll need to go scroll down, go to the material section, and in the material section, you need to define one material, something like this. And you need to use concrete properties for these, or concrete parameters. These parameter that we have used is for the 48 grade concrete, or 48 megapascal of megapascal strength of concrete. So you can use some different concrete grade, and your parameters, your constants will vary. But this is how it is implemented. Once you have used these parameters and you have named this material as ABQ_JH2, this command actually invokes this material model. And then I have named it as a concrete, and then you need to assign this material to the section we had already created for concrete. And then you can go ahead submitting the job using command window. I hope you like it, and I hope this will be very clear to you. But in case you have any queries regarding this, you may reach out to me in the comment section. Thank you so much.